Okay. So today we'll understand few concepts. We'll understand the concept of worm, schema on read and write. We'll also look at data local processing network usage block and this throughput. So these are some of the big fundamentals which needs to be looked at. So first, let's understand schema on read and schema on write. So this is another big data concept where most of the places where we will learn, this is becoming one and more important popular. So here is the thing on schema on read and schema on write. Let's talk about an RDBMS situation. And you have a project and you want to fit your data into RDBMS. So this is your data. And this data, data has a lot of fields like, let's say, employee details, the customer relationships detail, the sales details and so on. So all that detail is here. Now you want to build a data warehouse, let's say, for current assumption, you want to build a data warehouse, maybe in an appliance or in a RDBMS. So appliance would be like Netezas, Teradata and so on. Data warehouse, the RDBMS would give an Oracle and so on. So you could build a data warehouse using either of those because they are still the same relational construct. They support relational queries and so on. So if you have to do this, the first step which you do is you understand this data and do a data modeling. You understand the data, you do the data modeling, you arrive at the star schema basically. Star schema is a modeling technique where the model will consist of dimensions and facts. So you have dimensions which are attributes which defines the facts. So you have if you have to do this, you are going to do some data modeling and basically define your schema. Right now it can be in the form of star schema or third normal form or anything. So but you will do the model. Once you do the modeling, you will build the database with the schema. So this would be your second step. Once the database is built, the next thing which you would do is you will load the data, load and transform the data first. First you will not even load, first you will extract the data. Then you will transform the data and you will load the data. Okay. So somebody asked what is a schema. So let's say if it is a sales data, I want to create a table called sales. Then I will say which geography this sales came from, and I will say geography is of type string. Then I will say, okay, this is going to come from particular region. A region is of type string. The sales which has come in is of amount, let's say double. So the definition of this, that there is a table sales, there is a field geography with which type string, there is a field region of type string or a field sales of type double. This is what is known as schema. So now you have the sales table, you will also need a customer table and you will link sales and customers because in this case the customer is a dimension, sales is a fact, and when it is a fact this schema will not be like this, but assume it. So this is what is known as a schema where you are defining the data types, attributes and the data organization. Okay. So that's what it means by schema. Now when you are trying to do an RDBMS, taking any data and putting into a data warehouse, you are going to do the data modeling, build the database with the schema. Means first you are going to define this, then you are going to build it, okay, then you are going to extract from here, transform it to fit into this structure, and then fit into that. So this is called the ETL process. ETL, extract, transform, load. And usually tools like Informatica and others actually do this well. Informatica, Cognos, there is a couple of tools which actually does this very well. Okay. So in a traditional system, you are going to do this. You first define the schema, build the schema, and then extract, transform, and load. There is two important things to note. You have to define your schema upfront. Okay, define upfront. Second, you have to transform your data upfront. If you are going with traditional approach, you are actually transforming your data upfront. So for example, let's say this sales data is in double. So this field which you have here, okay, let's say it is a string. You move it to this field, convert that string to double before you put it in there. So that is where I am saying you need to transform your data upfront. Okay, and the data will be stored in the form which this database understands. So database will be storing the data in a form of files, and that file will be only understood by the database. So database, what it does is it transforms the data and stores it in its own form. So that's what is the case when RDBMS is there. When you are on the big data systems, you don't define the schema very rigidly. You can define it, okay. So it could be okay that you define the schema, but you never transform the data upfront. Never transform the data to fit to the schema. What you do instead is, when you read the data, then you dynamically transform and extract the required fields, and I will explain you this. And this is known as schema on read. Okay, so schema on read means schema validation on read, or schema is applied on read. In this case, schema is on write actually. So let me explain the difference. When we are writing into the database, you transform and validate the data to fit to the schema. In the case of a big data, when you store it, you never validate the schema. When you read it, you enforce that it is of type double or string or whatever it is. So when you store it, you just store whatever you get it, raw data as is. You don't do any transformation or anything. You just dump the data, and when you actually want to read it, you transform the data. Now there are many reasons to do that. So here the process will be, you define the schema to some level. It is not required that you have to define it to the last level. Define to some level. You move or dump the data and basically forget it. When you want to read it, it will transform, it will validate the schema and give back the result based on the schema, based on the predefined schema. Now, why is this done? Because in big data we said that data can be of different types. It can be structured, it can be unstructured, and so on. Okay. So it can be in different forms. Now, one way is that you define a schema, you transform all the data and put it into a big data platform. But it is known that if you have a big data, many of the data attributes will never be used. So you don't know which attributes is going to use, which you are not going to use. So it is not worth to do transformation upfront and process it and keep it, because it will take long time to do all that. You are just wasting your compute when that whole thing is not at all required, because 99% of the time nobody uses it. It's only 1% maybe somebody wants to use it. So the best way to do it is just dump and keep it. Whenever you need it, let the parser go through, let it parse the whole thing, extract it and render. So the whole idea is that do you spend your time processing upfront, or do you spend your time processing later? So in a big data approach, the processing is usually done later. It's not done upfront. Okay? Who is this guy? So continuously. Okay. So there are 2-3 questions here now. We will answer all of those questions. But fundamentally, you need to be very clear that in a traditional system, you define the schema and then you transform the data and store in the database or wherever it is. In the case of big data, you define the schema, but you might not transform the data. You will just dump the data, and when you want to read it, you will parse it and read it. And the huge advantage for that is 90% of the data might not be really required to be parsed. Whatever you need to be parsed, you need to be parsed. So that's the only thing. Now, why do we do this? Because the different types of workload exist. In RDBMS, whatever you store, there is high probability that you are going to use it. While whatever you store in big data, there is a high probability that you might not use it. So given that is where the philosophy is applied. Because big data is also more looked at as a dumping ground to store the data, so that in future whenever you need it, you have the data available to you. So since it's also more futuristic, spending the compute upfront might not be a wise investment. Second thing is the organization of the data into third normal form and others are not done in big data. It's a raw data. Okay. So why we don't organize the data in third normal form or star schema? Because each of those are optimized for certain solutions. Like a third normal form is optimized for transactional system. A star schema is optimized for data warehouse kind of system. Now, when we come into big data, you don't know what type of data is going to be used for when. So that is the reason you really don't want to do your upfront processing. Okay. So now I'll answer a couple of questions. So the first question is, what is that some level of definition? Okay. When I say some level of definition, it is, first of all, there is no relationships which we are trying to define here. Okay. No relationships between data. You don't define any relation in big data. You just take each data file or each data as a single entity by itself. The relationships are built on the fly. dynamically. Okay, so that is one thing. Second thing is, it is not mandatorily required that you have to only define one table or one definition for it. Okay. For example, let's say I have an employee file. Okay, so let's say I have an employee file and it has some format, 1, 2, 3, 4, 5. So some format it has. Now in an RDBMS, what happens is each of these fields is extracted and stored. So the RDBMS precisely knows that yeah, it has a field called employee ID, it has a field called, let's say, age, and so on. Okay. On the other hand, in big data, we don't extract the field, we just store it directly. Okay, so we just store it, dump it. So tomorrow you could actually view, let's say, the employee ID and age as one field. For some reason you want to build employee ID and age as a single field. Let's say call employee's new ID or something. Okay? Which is possible because all you are doing is you are not transforming the data upfront. You are going to dynamically apply your schema. So you can apply any schema on that file the way you want it. Okay? So there could be multiple views on those files which you can create. While on the RDBMS, once the fields are defined, the way you parse the file is predefined. Here you could use a regular expression to parse it and so on. So there could be many things which you can use to parse the file. So that is one more bigger advantage. So I am saying that you don't need to define any relation. Similarly, you can have multiple views on the data, not just one view. The first view was saying that read this field as employee ID. You can have another view saying that combine both this field and read it as employee ID, new employee ID, and so on. So there could be different forms of how you read this data. So this is why I am saying that you can define at some level. You don't have to define it very rigidly. Don't define anything rigidly. It has to be flexible. So that's where I say define the schema to some level. Make it flexible defined. Okay. In RDBMS, yes, once you define the fields, you can have to read it that way only, or you have to create a view, but the fields will still be the same because the data is organized in the form of every field. Okay, so that's how it is done. So there is one question here. Why do we need to transform? We can just extract the fields. Yeah, so extracting and transformation are going together. In this case of big data, we don't even extract. We just dump it. There is no parsing of the field which is going to happen. In the case of RDBMS, you are going to extract the data from the source system, transform the data. You can call transformation as not required, but I can just extract, which is fine. But here you don't need to do anything. You just directly dump the data. Now there is another question which says, so in big data, is it mandatory to define the schema at some level? To some level, yes. But you can define the schema very vaguely because you are just dumping the file. You can say, forget all the fields in here. I am not going to look at any field. I am going to say it is a common single field. It is a single line. I can define the schema that way. And I can read line by line and parse it in my query itself. So all that can be defined in big data. In the RDBMS side, you cannot do any of those because these are all rigid and fixed. Okay. Yeah, schema can be for any form of data. Okay. So you can have a unstructured data, you can have a structured data, and so on. See, you can, let's say you have a video file for now. Okay. video files are going to be consisting of frames. Frame by frame you have some data. Now you can store the entire video as just as a byte sequence basically, or you can store the frame by frame as a byte sequence. Okay. And each frame you can number it and store it in some form. Okay. So this is the entire video can be stored in a form of a byte. Or you can also define the metadata about the video, like who created it, when was it created, and so on. So this is going to be your schema on a video. Even though the video file was very unstructured, you started defining some form of a structure to that. Okay? So this is what is called as some form of structuring. It is not like very rigid. I can define something so that I can use it to read it. So if I have to interpret a video, I would rather interpret frame by frame. So I would just say that, okay, video consists of multiple frames. Frame 1 will go from this byte to this byte. Frame 2 will go from this byte to this byte, and so on. Okay. So that is what we are defining. Okay, so I hope everybody got the idea of schema on read and schema on write. So the key thing to remember is, in a big data system, you never parse the data upfront. You just dump the data. When we want to read the data, that time we apply the schema and the parser. Basically, you try to use the schema and parse it when you really need it. Otherwise, you just dump the data. Because majority of the time, it might not be used. And we should not waste our upfront processing power when it is not really required. Okay. So that's the first concept for the day. Yeah, anybody has a question?
Yeah, I have one question. Can you hear me?
Yeah, I can hear you.
Yeah. So I wanted to know in a typical organization, how they control the data. I mean, how they control the metadata of so many files coming in and out of Hadoop. And do they really control it? And do they really maintain any lineage? So in ETL world, we see the ETL tool has a little lineage functionality available. So do they have, I mean, is it really required to try to maintain a relationship between multiple files and try to get a lineage out of it? I mean, usually, is it followed in the organization or not?
Yes, so this is a good question as such. So from a schema perspective, yes, every organization is coming from the traditional world. So they are used to this star schema, relational schema. There is a specific modular job and all of those in the organization. So when they come to big data, there is a bigger cause of concern, saying that now data modeler doesn't have control over all the schema. Developer is going to define a schema and use it wherever he wants it and however he wants it. So how do I enforce a data governance on the whole thing? How do I know which field is going to get derived at what time? Because it can be derived dynamically. So it becomes like a developer's paradise versus a modeler's governed strict governance which is there. So that's the trade-off which we went into. So what enterprises today do is, instead of tracking all the fields, all the stuff exactly as you would do, you could still do the same thing here, where you will organize the data in the form of files. Okay, so if for each file you will have the metadata, like where this file came from, where it is going, what is the content of the file, what are the potential fields of this file, and so on. So you define this metadata and you govern this metadata. So that is still there. The only thing which is not happening is you are not parsing this file. The metadata is getting defined and it is used to be managed. Okay. So people currently uses their existing modeling tools and all to manage it. But big data also has tools like which are coming up with metadata management. In the Hadoop ecosystem itself, there is a tool called H catalog. This is called the Hadoop catalog. which is used for metadata management. Again, it's not the kind of a master data management solution or the metadata management solution, but it is a reasonably good metadata catalog. Similarly, we also deal with what is known as metastore going forward, and this is used by an entire ecosystem where the metadata of all this data which is stored in Hadoop is stored. Okay. So we will come to these things in the subsequent sessions when we cover those. But yes, there is concepts of metadata, there is concept of management of the big data, but at the end of it, it's still a developer's paradise. You cannot strictly enforce anybody to do anything, because once the file is available to a developer, he can define his own schema the easy way and he is going to read it and use it. Okay, so that problem still exists. So Dipta, I hope that answered your question.
Yeah, thank you. Thanks.
I didn't hear you, but that's fine.
Yes, thanks. Can you hear me?
Okay.
Yeah.
So going forward, let's go to the next concept. So we are trying to get each concept right. Now we have got schema on read, schema on write. Yesterday we said that we should not move the data out of the place. We should, in fact, the code is lightweight, so it is better to send the code towards the data rather than move the data out and use the network latency. So that is the second one. We should always try to do within the local data. We should not try to move the data across, because network traffic is going to create a lot of bottleneck for you or latency. Okay. So now let's understand this throughput. This is the concept which needs to be understood. So now let's say you have a physical disk. This is your hard disk. Okay. So this is a physical disk. Let's say this is a 2 terabyte drive, and it's usually the specification will be like 2.5 inch SATA drive. Okay, so depending upon whether it's 2.5 or 3.5, these are the two form factors that drives come in, and they also define what is known as the RPM, 7.2 K RPM, let's say. So that's they define most of it like this, because these are like disks which are not really solid state disk. It is the normal disk which we have. Okay. Now, what is if I have to read the data from this disk, there is some bandwidth which is available to read it, because every time when you try to read a data, there is IO bottleneck which usually happen, and this is one of the biggest bottleneck when we try getting into a performance tuning of any application. That reading data from the disk is the most inefficient thing in the whole ecosystem. After the network latency. Network latency is definitely there, but other than that, reading the disk data from the disk is the biggest problem. So let's say this give me 1000 Mbps or 1 Gbps basically throughput. So I can read at 1000 Mbps from this particular disk, let's say. So essentially my transfer rate is going to be dictated by this. I cannot go beyond this because the disk is defined. The disk capability is defined. But I want to process much faster than this. So what is my option? I can bring one more disk of same. Okay. So let's say 2.2 TB SATA drive and with 7.2 K RPM. I have one more 1000 Mbps drive. Okay. So what essentially means is let's say if this is my processing unit, okay, this is my processing unit. If my processing unit is able to process more data, but I/O is becoming a bottleneck. If I read from 2 disk drives, the throughput actually increases or doubles. Approximately it will double. Now you will say, okay, if we need more throughput, we can put a more disk. But it is not going to be always efficient to go a large degree. At one place, the saturation of the processing unit is going to happen, where even though you have more throughput from this side, the unit is not able to handle it. So that is the sweet spot which we need to reach to. Okay. Now the question is, traditionally we have been storing the data in one disk, let's say. We were storing the whole file into here. Let's say I have a 750. So let's say I want to store a 1 GB file. It will take a very small file. 1 GB file I want to store it. So this, since 2 TB is there, if I have to store a 1 GB file, I can store 1 GB here. Now, even though I have more drive attached to it, it is of no use. When I have to read the file, I have to read it from this one drive only, and the bottleneck is going to come as 1000 Mbps. But what if I break the file and store it? If let's say I store it into 0.5 GB here, and the same file, so I will cut this file into 2 pieces and store it. So let's say I store part 1 and part 2. The part 1 I store it here, and part 2 I store it here. So you can see that automatically the throughput of reading this file has doubled. Only thing is, on the processing side, he needs to manage that this part of the file should stick below this file, so that you won't get the whole file as such. So there is a slight overhead in processing, but you increase your throughput by almost double. And if you have more, if the CPU is still able to handle, maybe you should add more. So instead of putting 0.5, I would rather put it further down. So this is what is known as parallel disk. Okay, parallel disk increases throughput. Not just throughput, you need to ensure that parallel disk increases throughput once you store files in a distributed form. And this is basically what they are trying to do, even with RAID and others, that they are. So if you look at a RAID system or a disk array system, so not a RAID system, I would say a disk array system. So they have, let's say, a SAN storage attached to the network. Okay. So you have different disk arrays. So this is not a rocket science anywhere. People understood that long time back. But what they did is they created SAN arrays. Okay. And now the throughput provided by this particular SAN is much higher than individual disk. So these are all individual drives. Okay. So this is how the principle of SAN works, that there are so much of disk arrays which are there, and you have a higher throughput coming. But the problem in SAN is that you keep it in the network, so that you have to go through this network. So the network latency becomes a problem. Okay. So throughput will be high here, but problem is network latency will come. What Hadoop tries to do is saying that in the same node where you have the processing, in the same node, you start attaching the drives. Instead of keeping the drives parallel in some other place, you take drives and attach it directly to the processing unit till the capacity the processing unit can handle. So you eliminated first the network bottleneck, then you increased your parallelism or the throughput, by adding more disk in parallel. This is another important concept you should remember, how Hadoop is little different than the rest. And when you say Hadoop, we never recommend that you use a network disk. We should always use local disk, and not one disk, we need to use multiple disks. Any questions here? I don't see any much questions, so let me see. Yeah, we are all clear. I hope this concept is really clear. Okay, so this throughput is another thing which you need to remember. Now let's look at block storage. So next thing is block storage. So these are all one by one concepts which are used in the big data systems. Okay, so that you know that big data system is optimized for bulk data. Big data system is optimized for large data. So it is also optimized for fast data. So optimized for bulk data. So let's see the situation again. Why block storage? Now I have a file. Okay. Now I can store it in record by record form. So 1 record, 2 records, 3 records, 4 records, and so on. Okay, so like record by record. Each one is a record. A table has multiple records. So similarly, if I can store record 1 separately. I have record 2 and so on. So when you look at it, in this data when it is stored in the disk, okay, so let's say an RDBMS is storing this. So what RDBMS does is, RDBMS stores the data as records. 1 record somewhere, another record somewhere, another record somewhere, and so on. Okay. So this is RDBMS. But what RDBMS will do is, it will keep the pointer to the beginning of the record somewhere. Okay. So an index is created and pointer to the record is maintained. So that is how it is able to traverse. So if you ask for give me where record equal to 1, it knows that okay, record 1 is here. So I will go and read from here. The record 5, I know it is here, I will go and read it from here. That is how the index is done. Okay. Now this is good when you want to read by record. So you read by record in the sense that you are saying that give me the first employee. Then you are saying give me the 55th employee. Give me the 27th employee, and so on. So I am going to read by a record. So in that case, this storage is very efficient. But let's say in a data warehousing world, I am saying get me the sum of salary where age greater than 25, let's say. So there is already an index which will say, if in an RDBMS form, there will be an index for the age. So you will say age equal to 1, these are record 1, record 2, and so on. Okay. This is how the index will be there. Age equal to 2, let's say there is record 5 and record 7, and so on. So it will have pointer to each of this record. Let's say age equal to 30, there is bunch of record. Let's say record 9, record 10 and so on. Okay, so this is the index basically. So when I have to run this query, first I will go and scan all the records of all the indexes keys which are going to satisfy this particular query. And then I get all these records individually, go to each record individually, pull that records and then do sum of salary and get it out. So this is how an RDBMS will work at a high level. Now, if this is going to bring up, let's say 60% of the data, we are still going every record at a time trying to figure out and get through. So for every record, there is few things which you need to do. First, there is an index lookup. Then you have a record seek, basically searching through the disk to go to that particular offset. Then you read the record. This is your sequence. Do an index lookup, find the records offset, go to that position on the disk, read the whole record. Now let's say there is some numbers which you want to associate. Let's say the record index and seek, let's say it takes around 1 millisecond. Okay? And reading the record takes, let's say, 10 milliseconds. So basically, so this milliseconds might go to nanoseconds or whatever it is. Huh? Just right now, just assume. Now what happens is, for every record you are spending 1 millisecond and 10 milliseconds of read. Now since the volume is less, okay, let's say I am looking at a 1 million record. Then I am looking at close to around 1 million into 1 millisecond. So we are looking at 100 seconds which will go there, correct? 10 raised to 6 and into multiply 10 raised to 3 will go. So 10 raised to 3, so around 100 seconds you are going to do an index lookup. You are going to do much more time spending reading the data. Okay? So let's assume this is what you are going to do. What if, so there is going to be a significant portion as the volume increases, there is a significant portion of record seek time which you are going to spend. Obviously reading the data is going to spend much more bigger than that, but you cannot avoid that deal because that you anyway have to read the record. There is nothing much you can do about it. That is the physical access time which you have to spend. But this seeking the record can be definitely avoided if I store all this as a single record while I store it only. When I store it, I can store this as record 1 or I can do it as block 1. So this is where the concept of block storage comes into play. So if I store it as block 1, the index which I need to maintain is only for a block. I don't need to maintain at record level. Obviously there is a definite disadvantage because now if I have to search by a particular record, I cannot do it. But if my majority of the queries are going to read anyway majority of the data, doing it through block is much more efficient than doing it by record. So that you can eliminate this whole multiplier because there will be only once which you are going to seek the block. You will seek the block offset once, then read a contiguous amount of data, and in memory you are going to split the records one by one. So I'll say record 1, record 2, record 3 is going to be split in memory after that. So this is the concept of block storage. In block storage, the granularity of storage pointer is nothing but a block which is having multiple records stored contiguously. Okay? The whole idea is to eliminate the seek time. Any questions? So this is another important thing which we do in big data. Because in big data, most of the time is we read the entire file. So if I am anyway going to read the entire file, there is no point restoring in record by record. Instead, I can read the whole block, parse the block to get the repeat. That will be much more faster than pending the record seek in database or basically the disk. Any questions?
So this one question.
Yeah.
So how you will be grouping the data to store in the block level? So in which will I'm not getting it. So how you
So I
will
am not going to group the records. Let's say I am getting an employee file. Okay. So let's say this is an employee file. So if I am getting an employee file, if you go back earlier, I am not even doing schema on the schema on write, correct? So this is like 1, 2, 3, 4. 1, 2, 3, age, let's say gender, male, salary 200, and let's say address, some address is there. Okay, so this is one record. Now this is another record. So I am getting fields like this, let's say. What I am saying is, I am not going to worry about fields. I am just going to say, let me take the first half a gigabyte like this and store it as block 1. The rest half I will store it as block 2. Now I know that when I have to read the employee table, I need to read almost everything all the time. So I am going to say give me block 1 and all this data will come. Okay. I will say give me block 2, then rest of the data will come. And I know how to parse the file separately. That is schema on read, which we have already defined. So I have read the data. I will apply my schema on read to parse the record. Okay. So this is how it will be stored. It will be first, the input data file will be broken and stored. Okay. And when you read it, you are going to read block by block and then parse the whole thing in memory. Is that clear, Jeevan?
Yeah, it's clear, Satish. Thank you.
Now, how is the blocks defined? Yeah, blocks defined when we go to Hadoop. There is a way to define the block size and so on. And it is something which you as a architect or you as a system admin can be defining the block size. So it's a trade-off. I can keep the block size bigger, okay, and that we are going to come next. How do you define a block size? What is the trade-off between a block size and many things? Because there's a parallelism block and all of those which we are going to come to. For now, assume that admin is going to define it, and it can be defined for a system. So when I'm using a system, big data system, for a Hadoop, I can define my own block size. Okay. And what are the criteria to define that block size will come.
Okay, fine. Thank you.
Yeah.
It's kind of related. So when you are defining a block by its size, so are you also controlling one particular record should not go in two different blocks?
No, we are only controlling block by the blocks can be broken into multiple. The record will be broken. That is possible.
Yes, I mean 64 might end at the 50th record, half at the 50th record, right?
Correct. It will end it here. Yeah, it might end it like this. This much might go into the next block.
Yes, that is possible.
Yeah, and that is exactly the way it is stored.
Okay.
So when you store it in blocks, you don't worry about record. Okay. Now the question is, okay, if I don't worry about block, how is it going to happen?
Yeah, I mean, so when you are going to process this block, it's going to be a problem, right?
Yeah, it is not a problem. We will have to handle that.
Okay.
So when you go to MapReduce, you see that it will handle it.
Okay.
But physically it is how it will store. It will be broken. Okay.
Okay.
So there is one more question which was there on the screen, which is, one more thing which you need to remember is that since we are just dumping the data, okay, in big data system, so let's say your file can have, let's say, 20 fields, okay. So, but you are interested only in 5 fields. In an RDBMS, what you would do is you will parse it, split it, extract that 5 field and put it. Okay. Tomorrow, let's say you want the 6th field, then you are in trouble, because now you have to go through the whole modeling exercise again. You have to go to the data modeler, add the new field. He will decide which schema, where, which field, how will it put. Then you have to alter the table. Then you have to change your ETL load process. So the agility which you have in your traditional systems for new data is very low. So agility for new data in RDBMS is low, means new data or new field, I would say. You have to do a lot more work. On the other hand, if you look at from a big data, there were 20 fields, I only needed 5 fields. Okay, I didn't parse this file at all. I just dumped this file into my big data system. Just dump this file. I am not even parsing it. I am defining the schema of for only 5 fields at today. So when I read it, it will only parse the 5 fields. Tomorrow you come and say, oh no, I forgot one field. Can you add that one field? What I need to do? I just need to define one more additional field and say, oh yeah, here you go, read it. It will read the 6th field. So agility is very, very high in the case of schema on read. So if you apply schema on read, agility is very high. When I say agility is high, it means that flexibility. Okay, it's very high. Now, extrapolating the same thing here. Here, whether it's 5 field or 20 field, I don't really care. I am only worried about the block size. And it might break anywhere. So, the idea is that the storage is not decided based on the fields. The storage is going to be decided based on the size of the file which we need to read it at one time. And that's called the block size. So why you need to do block size? Because you want to avoid the seek time. So now you need to combine all the three: schema on read, block storage, and disk throughput. So let me go to the disk throughput one. You can see now all the three in action. And that's how you are gradually building the system. So these are all things which are required for. So you saw that now here I had used a block storage to break the file into blocks, and I have read it here. And then here I have done the parsing in the processing unit. Okay. So I got parallelism, I got block storage, fastness, I got flexibility by parsing at the processing level. I hope you guys are able to tie it all three together. I also avoided network latency. And I am saying that any processing which needs to happen will happen here rather than pushing the data from here to somewhere. The data, only processed data will go out from here. No raw data will go out. So that means we have taken care of network latency. We have taken care of throughput because of I/O bottleneck. Okay. You have also taken care of reducing bottleneck because of seek time by doing block storage. We also got flexibility by schema on read. You need to put it all together. And this is how the system is gradually getting built. So you see this, whatever we are discussing is optimized for large data read, bulk reads and bulk writes. So this is optimized for certain workloads. So which essentially means you should not look for using the same solution for everything. It is not a solution for everything. It is optimized for bulk workloads. I hope this is clear.
Hashudish, Karthik here. I have a question. In the previous picture, you mentioned that the block storage size is 0.5 GB, right? Say for instance, like initially they define the block storage as 0.5 GB. In future, if they increase the block storage size to higher level, and if we increase, what would be the impact?
Yes. So let's go to the next thing, and that will explain you what is the impact of changing something in the system. Okay, and then we'll come and answer that. So we are on to the concept of worm. So let me finish worm, and then we will answer your question. Okay, so that will make it very, very clear. Worm. Worm means write once and read many times. So usually all big data system is optimized for this. Okay. Now, how does this relate to Karthik's question? Karthik is saying, okay, I had actually stored my data in 0.5 GB block for now, let's say. Okay, so he has stored his data in 0.5 GB blocks. So when the first time he came in, he decided, okay, all these nodes are going to store 0.5 GB blocks. So we went ahead, we created these blocks of 0.5 GB. Now all of a sudden somebody new guy comes in and says, no, this is not an optimized day. I want to break this into, let's say, 0.25. I want to make it to half of it. That's what I think that is the right block size. So this guy comes and says, okay, I will do it at 0.25. Okay. Now, what happens in a Hadoop system? In a big data system, it's always write once, read many times. Which means, whatever you have written here remains as is. This change can be applied only for newer stuff. You cannot apply, once the thing is written, it's final. In big data systems, you don't go and revisit the data again and again and rechange and do and so on. In the case of RDBMS, let's say you have a record 1. Now, you have record 1, let's say, and it has, let's say, 4 fields. Record 1 has 4 fields. Employee ID, let's say 1, 2, 3, 4, age 25, gender, let's say male, and salary, let's say 200. Now, after some time, you want to change this record 1 to 1, 2, 3, 4, let's say his age changed to 25. Now, this is what you want to represent in your database. What you will do, you will just fire an update query. In big data, there is nothing like an update query. You cannot fire an update. So when you want to make this happen in big data, your system write once, read many times. So this file would have gone. You would have stored this. When you store it, you will say that this is version 0. When this comes in, you will store the same thing with version 1. So in Hadoop and other places, you are going to do append. This record will go and sit next to the, it is an append only thing. It is never a overwrite, or it is not a update on the existing data. So it's always an append which you will do. So that is where you will have a history which is there in the case of big data system. And that technique is basically what we are talking about, write once, read many times. Because in a big data system, the workloads are always defined to be written once and read many times. This goes back to our dumping philosophy. Any data you find in, don't throw away. The data is a gold mine. Just dump it here. Anyway, that is why you write it once. And you can read it many times. Now, there is a question.
Hi, Sudesh. Sorry to interrupt. You answered my question. There is one more question right now I have. Say, in this case, you consider record 1 and you are changing the age of an employee. Okay. So in big data world, you store the data as a block. So considering a block, we have 100 records and it holds this record 1. Okay. So now the age of an employee got changed. So again, it's an append statement for this employee and it's stored as a version 1. So my question is here, like, will it store the entire block in a new distributed system and it's keep the version V1 for this record 1, or it's only consider that particular record 1 in a new block?
So there are multiple things. By default, Hadoop doesn't support versioning. Okay, versioning is something which you have to build. What I am trying to emphasize first is, once a thing is written, it is written. The only option you have is to version it. So you need to build a logic to say that, okay, next time, anytime a record changes, I'm going to take all the records which are changed, I'm going to associate a version to it and put it. Hadoop by default is not going to give you anything for this. Okay, so updates are one of the biggest challenges Hadoop, because Hadoop is only append only. Okay, so what we are saying is that if you want to change any data in Hadoop, you need to build your own system to do that, or your own logic, business logic to do it. Hadoop at its core is going to say that you have written one block, you tell me, you give me one more block, I can store one more block. Or you can tell me delete the previous block, I can delete the previous block. So there are two options. I can say that, okay, I will reconstruct the whole block. Okay, I can reconstruct the whole block. I can then delete the old block and create a new block, replace it with a new block. This is possible. Okay, this is option 1 to handle version. If you are handling version, this is option 1. The other option is, I will say that, okay, I don't want to delete and all, it is because I have to reconstruct the whole thing. I am going to do option 2, in which I will always have a record identifier, okay, which will identify my version, and this information I can store it in some index or something. Okay, I will say that version information is stored in index. Okay, and I will keep adding data. So whenever new data comes in, I am just going to add another block. That's it. And update index. Now index is not stored in Hadoop. It might be stored in some form, in memory or some other place, where update is possible. Okay. So what you are going to do is, let's say this is the employee ID. So I'll say employee ID 1, 2, 3, 4. It is in block 1 to begin with. Okay. Now you want to update it. You update it and this is stored in block 2. All will go and say that employee ID is in block 2. So now whenever you want to fetch the record, you can go to this index. Oh, I have to fetch from block 2. So you'll read the block 2, get the record, clear it out. So this is your one of the other versioning technique, but you will have to build this logic. So whenever we say Hadoop doesn't support update and you want to build an update logic, something like this you will need to build. Okay. So it is not by default giving you this capability. So you will see that in HBS and others, this kind of capability is already built in by the system, and hence you are able to use update in that systems. Okay. Any questions?
Hey Suresh, this is Sandeep. I have one question.
Yeah, Sandeep.
Earlier you explained about the concept of network latency, throughput, seek time, etc. So these are optimized for large data set, but in case along with large data sets, if we have a lot of small files in the system, does it impact the processing of those small files?
Yeah, so what happens is it's not about large files, small files which we talk about. But if you say no, my files are going to be 100 MB, okay, I have a problem. So if your file size are 100 MB, what we recommend is you combine many files and zip it, basically. Zip the file. Okay. Now your combined zip file might be higher. And Hadoop and other systems are capable of understanding the file format and uncompressing and actually getting it from there, which you will see eventually when we study the compression formats in Hadoop and so on. This is one technique which you can use. If your files are smaller, what you do is you combine the file, zip the file and create one file and use it. Now there is a trade-off, okay, and which you will understand that the moment you combine the file, you lose on your parallelism, and which I don't think you will understand today that, but we will come to that. Remember this and ask me when we do after the MapReduce, you can ask me this question. So when you combine the files into a single file, what I'm making one statement that you will lose your parallelism compared to processing these in 100 MB in parallel, because now you can only process one zip file. So it is at the compromise of parallelism, you would usually combine the files into a zip file. Okay. So I hope, Sandeep, that answers your question, that how do you handle small files? You basically zip it and you handle it, but you need to be aware that the moment you zip it, your parallelism is going for a toss and you need to be worried. Okay. Any questions? Okay, so we covered most of the fundamentals. I also said Hadoop is append only. It writes once and reads many times. So these are all fundamentals for large scale data processing. Schema on read, network latency, they move data towards the code, this throughput and all of this. So you should know about all these fundamentals when we are looking at big data. And please don't forget this, because anytime you have a fundamental question on performance or throughput or reliability, you come here and see which of this principle I am violating. If I am violating any of these, your performance is going to go down, your throughput is going to go down, and so on. So when you are, let's say you are an architect and you want to evaluate an architecture of a big data system. Some guy comes to you and say, I have this fantastic big data system which I have built myself. Now your question would be, is this system scalable? Is this system reliable? Is it going to be flexible? How do I decide it? You will evaluate some of those on these parameters and see where is the trade-off happening in the new system. Okay. So we have not covered some of the other fundamentals here, which is failure handling. Okay. So you know that distributed systems will fail. So there is no question of not failing. Okay. So let's talk about failure handling. So these are something which you need to evaluate when you are evaluating a system. You need to understand how do you do failure handling. So one of the technique for failure handling is, let's say you are storing data in a disk. The disk can fail. Correct? So what we are saying is, if disk can fail, the best technique to use is, what I am going to do is, I am going to replicate my data. So now if I replicate my data, even if one fails, I can pick it from the others. So replication is one of the mitigation for failure handling. And the default replication factor is 3. We restore at least 3 copies of a single data. And replication is done across the nodes, not on the same node. Remember that replication is always across the nodes, not on the same node. So you have the whole idea of replication is for failure handling. So when we are evaluating a system, always look at failure handling. Replication might be one of those. You need to do failure detection and recovery basically. So how do you do failure detection? There will be a heartbeat which is sent to the master all the time. So let's say this is the master and failure detection is going to be done by the master. In some cases it is a peer-to-peer architecture, and in a peer-to-peer architecture it is going to be each peer will detect it. This is a master-slave architecture. So there is a master and there are a bunch of slaves. So in the master-slave architecture, the heartbeat is sent to the master from the slave. So periodically heartbeats are sent, and this heartbeat is used to see the health of the slaves. And if the slave is not responding or is not alive, what it will do is, it will try to switch to the other replication. So failure handling has 3 things. You replicate the data, then you have to make sure that the health is detected properly, and whenever the machine fails, based on the heartbeat you will switch over to the other disk. So this is the 3 things which you need to remember when you are doing a failure handling. You need to do replications, you need to do a failure detection, and then once the failure detection happens, you should do a recovery. So this is another thing which you need to be worried when you evaluate this one. Okay?
So yeah, one question.
Yeah, go ahead.
On the replication side, actually, so if I am writing a block, so it will write into one node, then later the Hadoop will take care of the replication, or how it works actually. I'm thinking that if I am writing 1 terabyte of data, so the replication is going to happen 3 times. So again, it will be the network and bandwidth issues will happen, right? So just I'm not clear with that.
Okay, so the question is, won't replication impact bandwidth? Yes, it will impact. Now, how is it going to be handled in Hadoop? That we will see when we see the Hadoop interrupts. I have not even talked about Hadoop till now. Okay, remember. So don't think that I'm talking about Hadoop. I'm talking about general big data systems right now. So when we talk about Hadoop, we are anyway going to come and talk how Hadoop handles replication. For today, I'm just saying, won't replication impact bandwidth? Yes, it will. Okay, so the answer is yes. But how do you mitigate it? Because we are on the worm, right? Once many times. So we are only replicating once. So the impact is only once. So that is what we need to always see. It is not multiple times replication. Okay. So replication is only going to happen once.
Okay.
So yes, we are going to have this problem at once, and we will see how to mitigate that. See, there is one way, and I'll show you how this will be a good one to look at how internal of Hadoop will work, and we will do that later, but I just want to give you a hint of it. So you have a client. Now let's say a client is trying to store some data here. So there are 2 options. One is client starts shipping like this everywhere, all the replication. Okay? Or then when let's say when if client is doing that, The problem is the bottleneck will be here, because this data is going through a single NIC card here, and this NIC card is nothing but the network interface card, okay, where the IP is assigned, network interface card. So the bottleneck will be here, because any system can only send so much data out. It cannot send endless data, correct? So you will have this problem. So instead of doing like this, what Hadoop will do is, you give the data here, this guy will transfer, then this guy will transfer. So you are trying to use somebody else's bandwidth to do the replication. Obviously network will get choked, okay? But we would see that network gives you latency but not choky, because this is going to be usually a 1 Gbps or a 10 Gbps line, and on a 10 Gbps or a 1 Gbps line, the choking is not the problem. The latency is only going to be the problem. So choking is not the issue, it's going to be latency. And assuming that your NIC card on this machine is not choked. So since NIC card is not going to be choked, because we are going to use different NIC cards to do the transfer, your replication won't be too much of a problem. Jayvel, I hope you understand.
Yeah, yes, Sudesh, it's clear. Thank you.
So we talked about failure handling, we talked about replication, we talked about a concept of replication of data in Hadoop. Okay. Now there is one more big one which you need to remember is.
Hi, Sudesh.
Yeah, go ahead.
Sudesh, I have a question. Can you go to the previous slide, please?
Yes.
So in this picture, you say that client and we have slaves. Okay. Say for instance, the client wants to store 1 terabyte of data. Okay. So he transferred the data to slave 1. Okay. The slave 1 already stored enough storage. Say for instance, it has 5 terabyte of storage space, out of which 4.5 terabyte is already stored. So in this scenario, so slave 1 will good enough to store only 0.5 terabyte of data. So how would it transfer the data from slave 1 to slave 2 of 0.5 extra terabyte data?
Yes.
Will it be an impact?
No, that is a very good question, because that's not how it will do. So let's say this is your 1 terabyte file. Okay. So in a Hadoop, it will say I am going to, let's say, store a block size of 0.5 GB for now. Okay. So this file will be broken into 0.5 GB pieces. Okay. And the client is going to send only 0.5 GB here. If the other 0.5 GB, it will transfer here, and this guy will maybe transfer to the other. Then the next 0.5 GB might be going here, and then this guy might replicate other across. Okay. So imagine that there is a network of nodes, and the client is not just going to connect to one node while storing one file. It is going to connect to n nodes to connect and store the file. And how it will do? The master will instruct where to store it. So we will come to that when we look at Hadoop, that the master of the Hadoop will tell the client, for this block, store it first here and then here and then here. For this block, store it first here, then here and then here. For this block, store it here, then here and then here, and so on. So the order of which the client is going to connect is going to be decided by the master. So whenever a file stores like this, there is no problem of choking one particular node. Okay? Clear?
Thanks for this. I'm clear.
Yeah, so usually I don't wanted to cover all this right now. I wanted to cover when I was talking about internals of Hadoop. But that's fine. Since you have asked a question, it's better to clarify it right away rather than keeping the question for later. So with this you have actually got a lot of insights on how internally Hadoop is going to work. But we are going to take the whole thing up when we start with HDFS. Okay. But right now I am just still explaining at a conceptual level. We can actually see this in action when we go to the system and see how it is internally happening. We can actually physically see that block 1 is going here, block 2 is going there, and so on. We'll see that when we go to the next level. But for now, let me save this as failure handling, because the next important topic which we want to cover is scalability. Okay. So I hope till now everybody is clear. So we are going to go to the next topic, which is scalability. Again, somebody will be worried. We are not even talking about Hadoop. Don't worry about Hadoop. Once you know all this, Hadoop will be very easy. You don't need to, because all these principles is what it is used in Hadoop, nothing else. So if you know all this, you know by default the internal. So now after that, we just need to spend some time going through what is happening inside Hadoop. That's it. But all the principles are this. So big data or any systems in big data, you need to always think in scalable form. And this is one important aspect which you need to look at. You cannot say that I will not worry about scalability. If I don't worry about scalability, I have a bigger problem. So the fundamental concept around scalability is you use many machines to do your work. You cannot rely on one node to do your work. The whole idea is you need multiple machines or multiple nodes to do your work. So that is your first item which comes in when you look at the idea of scalability. Okay, you need more than one machine. That's the first principle of scalability. You need processing to be distributed. You don't want processing to be concentrated in one location. You need parallelism for all processing. When I say parallelism for all processing, I am saying that you need to ensure that any processing you do, it is not running a single thread and running at one place. It is running parallelly at multiple locations. This is something which you definitely need. Okay. So these are certain things which you need to always take care. That you are looking at multiple distributed systems when we are talking about scalability. Processing has to be distributed across the cluster. You need to ensure that no process is going to run at single threaded model. It has to be parallel. Then only you will be able to handle large volume of data. You will be able to handle fast volume of data and so on. Okay. So remember that scalability is one of the fundamental principles in big data. If you don't have a system which is scalable, it's not going to work. Now, there are so many things which you need to really look at. So there is a tech video in YouTube around Google. So you look at Google's Tech Talk, and there is a video on scalability. So please watch that video on scalability. It's a very important video. If you are into the big data space, this is the fundamentals. It talks about that failure is bound to happen. In a scalable system, failure handling is an absolute must. Nodes will fail, disk will fail, drives will fail, and it is not an exception that something is going to fail. Something is going to be failed is a guarantee. How do you gracefully handle is your skill. And when you are looking at scalable systems, the whole principle is around that you should not see saying that, okay, I am doing some processing here and it will succeed. No, it might not succeed. You should have a capability to schedule that processing here and being able to succeed. So everything which you do will fail. Everything which you do will crash. Everything which you do will not be reliable. So when you are thinking about scalability or building scalable systems, always think that these are going to be a norm and not an exception. So you basically code for all of this and get it done. Now you don't need to worry about all this if you are not an architect, because these are automatically built into the Hadoop system. This art of scalability is already inside Hadoop system. So as developers, as administrators, you don't need to worry about it because it's given to you. You just need to program Hadoop and you should be happy. But if you are an architect, you need to be worried about it because there are so many extensions which we do on Hadoop. Now as you design your extension points, you need to ensure that you are not violating any of the scalability principles. If you violate the scalability principles, then whatever Hadoop has done at the platform level is not going to help you at all, because you have built a system on top of it which is not scalable. So even though Hadoop is scalable, your target system will not be scalable. So this is only the message for all the architects to make sure whenever you add extension points on top of Hadoop, make sure that the fundamental principles of scalability is not violated. In the sense that you build something on top of it and you didn't take care of failure handling. You said that it will not fail. Then you are actually jeopardizing the whole system. The scalability of Hadoop is wasted now, because your system is now not fault tolerant. So please look at it from that perspective, because I know there are few architects in this session and they should be very, very clear that anytime I build any system on top of Hadoop, I know Hadoop is scalable. Anything which I build on top of it, I need to ensure that I don't disturb the scalability principles of Hadoop so that the overall system still be able to extend the scalability. So this is the art of scalability. Again, you don't need other developers, admins doesn't have to worry about it. The system will give you back. And for all those guys who are interested, please search for Google's Tech Talk video on scalability. And this is one of their oldest videos and one of the very popular videos on Tech Talk, which was something where they talk about the whole course on scalability. It's good. So this is all the fundamentals which we have. So now I am going to cover a particular use case. I will go and take.
Sudesh,
Yeah.
One question on scalability. So through the Hadoop, through the Hadoop, right, we can scale up the application in terms of multiple nodes, etc. But suppose we are getting a lot of files from upstream applications, and they need to be processed through client and then ingested into Hadoop. So client would become a bottleneck, or maybe a point where you are not able to scale up, right? So any suggestions for that? Like, should we have multiple clients, or what do you recommend for that?
So we will see that when we look at what is known as scoop in Hadoop. Okay. So scoop is tell that that scoop is the solution for everything. What I wanted to emphasize when we look at scoop is, so scoop is one of the ecosystem components of Hadoop, and what it does is, when you try to bring data into Hadoop, it is basically a tool which helps you bring data from RDBMS to Hadoop. And the problem is simple. I can always fire one query on an RDBMS, get my data and put it into Hadoop. Or I can partition the data, fire multiple queries in parallel and put it into Hadoop. Okay. Now, one way is I can launch multiple threads. Okay. I can launch multiple threads which can go in parallel and get the data. Okay. So that is one option. Or I can do multiple processes in parallel and get the data. So the art of scalability comes in using the right combination of process and threads and built-in parallelism, both at the client side and the system level, to handle this scalability issue, which essentially means in your case, when you are bringing the file into the system, first you need to ensure that the client is capable of running multiple processes, which essentially means there should be no state maintained within the client. The state has to be distributed so that many clients can use the same state. That is the principle number one. Second principle would be the client should be able to process in parallel. So it might be needed to have a multiple threads in place. The client should be able to launch multiple processes in parallel. The client should be able to launch in different systems in parallel. Okay? So if you have these three things embedded into your client design, your system is bound to be scalable. And that's the essential principle of scalability. And once you build that, immediately you have to come and say, did I violate any of the fundamental principles? Maybe yes, I violated failure handling because I didn't do any failure handling. Because in distributed system, failure is going to happen. So what am I doing to handle failure? So that's how you start thinking and you build scalable systems. I hope, Satdeep, that helps you.
Yeah, sure. Thanks.
So this is the way, this is the thought process. So again, what I want everybody else to know is, there are many books, there are many things which you can read, get all the stuff, you can do it. But you need to think the way I think. It is not that this is the only way to think. But what I really try to teach is, this is one approach to think in high scalable form. So if you understand the art of scalability, you will be able to solve any complex problem. So go through this thought process. It's very important. Why do I spend the time to tell you the fundamentals is, it's more important to understand why certain things is done the certain way. So that when you build a system, you say that, okay, I need to build it like this, then only it will be as scalable as Hadoop. So the whole idea is around that. Okay. So now I'm going to give you one more very important approach here. An approach to between traditional BI and big data. A new approach to doing things. Okay, so this is something which we will talk next. And maybe use case we will start from next time onwards. So let me just take few minutes to explain you the new approach to analytics. Approach to BI. Let's see. So again, this is a fresh topic. No, don't carry any baggage from the previous thought right now. This is a totally new concept. So let me breach this topic and we'll see how it works. Okay. So traditionally, if I have to do, let's say, a BI project, okay, I am doing a business intelligence project. What I will do, I will ask the stakeholders what kind of outcomes you want. Okay, he says I want this report, I want report 1, I want report 2 or insight 2. You can define anything. Report can be report, it can be dashboard, it can be insight or anything. I'm just going to call it as report 1 and report 2. What you would do, you would take this, say, okay, what fields are required for this report, what fields are required for these reports. Correct? So you will say, gather all requirements and fields for these reports. You got this. Then, once you get there, what you are going to do? You will say, okay, let me go ahead and do the data models. Okay. Then what I am going to do? Okay, now I got the data model. Let me apply the data model in the database and do the ETL process. First, go to source system, map the field, do the transformation, load my database. Right? So ETL process is loaded the database. Then I will say, okay, now let me go and build my report. Correct? build report. Then I'm going to do my testing. Anything wrong with this? Everything looks to be great, right? So I test it. And then I deliver. I implement and deliver. A typical life cycle. Implement and deliver. Any questions here? This is a pretty simple life cycle. Okay? From requirements to delivery, this is what you are going to do. Do we do the same thing in big data? Yes, many of them do it same. There is no difference because they come from the same background. They can do it. Nobody, no problem. But there is an alternate way also. So let's see what that alternate way is. So the requirement is clear. You cannot have any compromise there because everything starts with the requirements. You would have gathered the requirements. Now the fundamental shift starts from here. Do I model it? Do I do an ETL process? I already have a data repository. The data repository has all my data. If not, all I need to do is dump the data into my repository. That is what I would expect. So from all the system, dump the data into my repository. Okay. So I will short circuit all this process. I am going to directly jump to building my output. I will say, okay, let me build what I want. Build the report by extracting the fields dynamically. Because I can dynamically query this repository to get whatever fields is required. I don't need to do any modeling or anything. I just need to apply a schema. I'll just get on the field. I'll get it what I need. And I'll build it. I'll validate and confirm with the business user, saying this is exactly what you want and does this sounds good to you. The moment I get that, I'll say, okay, you got it. All I'm going to do is send it to production. I will productionize it. How do I productionize it? From the repository, I will maybe write a job which will spill out this report every day. Okay? And my production will happen. So if this is going to take around 6 to 7 months to do all this, this will be like directly on the report, you are testing the data and delivery. So dynamically querying the data using schema on read and delivery. So it is not to say that this approach is wrong or this approach is right. Now there is one important thing to remember, that business requirements are very agile. Here they will need report 1, report 2, and they might need report 3 and report 4, anything immediately. With this cycle, they will be able to see the outcome immediately, even though it might not be in a production environment. They will be able to see that results. They will be able to fine tune their requirements and do this iteration multiple times. So this is called the exploration process. So big data systems enable exploration. So you have an exploratory life cycle which is available to you. So use this as an exploratory life cycle and then go for a productionizing life cycle. Because many of the time after you have built it here, people realize this is not, it's waste, it is not giving anything which I am using. Okay. So the whole big data cycle usually lines like this. There is an exploratory phase where things will keep on evolving, and once that evolves, finalize, you productionize. So this is going to be the evolution factory which we talk about. And in the modern terms, this is where the people say, okay, we are hiring data scientists and doing exploration. Okay. So the whole idea is here that with the flexibility which big data provides it, where you can dynamically process large amount of volume on the fly, even though it might be repetitive, even though it might be, you are having the capability to process it very, very fast. You can do multiple iterations of this thing till you finalize what is really making sense and then productionize. So this is something, a new approach which exists there. It is not to say that everybody will adopt it. Those guys who are smart enough to use the power of big data will use this technique and become more agile in the whole world rather than going through this life cycle and keep on doing change request here. So this is more of a project level execution approach on how you do exploration and how you build agility into your whole information discovery phase. So this is what we call as the new way of information discovery. So in this, you explore or discover the data, and once you are done, then you go for the end-to-end use case. You don't really go for end-to-end till you have finished all your exploratory life cycle. And in traditional ways, your exploration was not very easy, okay? But in the new way, exploration is very easy. So in the big data analysis, this is the way. You dump the data into the repository, you ask your questions, you get your results. Once you know that this has to be productionized, then you productionize. In traditional system, you go through the life cycle, you build a dashboard, and then you publish to the business, and they say, oh yeah, it's good, it's not good. So the chances of failures are higher here, chances of success are higher here. I hope you guys understand the different philosophies of approaches of doing big data analytics, and you know which one to use when. Is there any questions? Okay, so we will go to stop here. So to summarize, I covered the fundamentals on big data. I looked at the traditional versus new approach of big data, and most importantly, we understand the philosophy behind high scalability, how to build high scalable systems. So this is what we have for today. So we'll go ahead. The next session is going to be on US Monday evening, which is India time Tuesday morning. Okay, and there will be a new invite. I will send you the rest of the details, everything, and it is not going to be on the same video meeting invite. Okay, I will send you the rest of the things later. Any questions? Yeah, all those fees and other things I will send you in the mail. So that's where I will tell you all the details. So don't worry. All that is going to come over to you over the weekend. Okay. So hope you enjoyed today's thing. You are able to get it. And I'm going to send you the recording for all of this. Okay. And yeah, Linux sessions we will have. We will be scheduling some Linux sessions next week. Okay. and I will let you know about that. Okay? Because what happens is from here, once you move into the more regular ones, you will have access to the systems, you have access to Linux, you have access to Java and so on, so that you should be able to do your stuff as we proceed. So that's the idea. Okay. So thanks folks. We'll meet again Monday evening US time and Tuesday morning India time.
Suresh, I have one question. If we're getting late, you can ask later on.
No, you can ask now. That's fine. I'm
Okay. So this is a pretty old topic. So I have read many places that Hadoop system is going to not going to replace data warehouse, and it's kind of complemented. So I just wanted to understand your thoughts.
Yes, and that is a correct start, and that is where I want to cover in the use case. Okay. So the next topic is going to be use case. So when we cover on Tuesday morning India time, that will be our first topic. Okay. The use case, what are the different use case, where Hadoop is applicable, where Hadoop is not applicable, and is Hadoop going to replace the traditional systems or not? It is not going to. Okay. And why it will not be, all that we will cover, because that's a whole use case story which we need to cover. So we'll cover that.
Okay, yeah, thanks.
Okay. So thanks folks. We'll meet on the next session. Thanks.